All right. Thank you guys for your patience with the clunkiness. It will get better. It just takes some time. Like even when I Google it and it's asked it, how do I draw a straight line on this? It says do shift, but that's not what it is. It does not do it on mine. So we'll figure it out. Okay. So we'll do the same thing here. I'm just gonna do a really lazy scale. Do 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 do. And we had 1, 2, 3, 4. Okay. So I know for a fact that this thing is gonna approach 3 from the left and the right as I get closer to x equals 2. So if we just go here, yes. So as x approaches 2, what does a y value approach? Good. So because there's a place where that's telling me what's happening along this vertical line, that's where as x approaches 2. But there's just another piece saying, hey, as x gets closer to 3, here's what it does. So we're just looking at two different parts of the graph, which does not look like that makes sense, but let's check it out. Let's deal with this one first, and then we'll tie them together. Okay, can we all agree that as I get closer to 2, it has to approach 3 as a y value? Now, theirs is boring on the key that we just saw, horizontal line. Doesn't have to be. Here's 3 right here. Could it do something crazy like this? As I'm getting closer to where x equals 2, is a y value getting closer to 3? And it does it from this side and the other side. Has to, because we see that limit exists. So all I can do is just this little section right here, and then I got to pause. Okay, we have this one knocked out. The limit as x approaches 2 is 3 of this function. Now, it might fill that point in later based on the other information, or it might be a hole. We don't know yet. Okay, what about as I approach 3 from the left side? What does it do? The y value approaches 3. So even like I just nonchalantly and just for no reason drew this kind of falling downward, but I know that as I come from the left, it goes back up to 3. Is that doing it? As I get closer to 3 from the left, it gets closer to 3 for a y value. Okay, so we got that one. What about from the right? As I get closer to 3 from the right side, and I'm just going to be all crazy with it, what value does this get close to? To 1. Does that get closer to 1 from the right side? Okay, so we've got that limit knocked out now. Addison, because it's telling me what does my function do when we get close to x equals 2, it's also, these other parts are telling me what does it do as x gets closer to x equals 3. Just two different places where we have a limit happen. Let's fill in the last little part. F of 2 is 3. Is that an ordered pair? So I'm going to go to 2, 3, and before I made the comment, we don't know if this is open or closed. Bless you. What is it? Open or closed? Closed. It is defined right there, and it happens to be there. Okay? This limit overall does not exist, but one of these has to be existing, and the other one's going to be a hole. F of 3 is 1, so I'll plot this point. There's my point that's defined, which means in the end, what has to be up here? A hole, otherwise it's not a function. Now, this is like with squiggly lines and being exciting, but let's just check. Exciting is not probably the right word. Does it match all these characteristics? Yeah, I think so. If we look back at what they had, they do the exact same thing, just a little less inventive. So here's their problem. Does that do the same thing as our graph, just without the squiggles? As we approach 2 from the left and right, it's 3. They filled in that point at 2, 3. And then as the limit as x approaches 3, from the left is undefined, from the right is defined. We have the same graph. Theirs is just not bendy and curvy. Cool. When I do these problems, it depends on the problem itself. This is usually where I'd start. I'd start with the f of 2 and f of 3. I'd plot those points, and then I'd go draw the limit stuff after the fact. But you can do it the other way, too. Is 39 also like this? 38? Okay, here's their graph. And just looking at this, without reading the book, I don't have a book in front of me, we're going to bet on the information that's given. I would almost guarantee that somewhere on 38 it says the limit as x approaches -1 is 0. And I know that because I'm approaching -1 from both sides. They probably never give me a defined point, or they say it's undefined, so I just use the open circle. What is the limit for this function as x approaches 2 from the left or right? -2. As I get closer to where x equals 2, which is this vertical line, we're approaching -2. You can do curvy stuff if you want, but as long as your graph shows getting closer to 0 right here, and getting close to -2 at that point, we're golden. Do you want to build that one together too and see if we have a different looking shape? Okay, I'm just going to do this one up here, and I think I can just draw on this. So let's see if we can't do the same graph And I'm just going to use a different color. And we use blue, apparently. All right, so let's pick our information. So let's try it the other way. Let's see if doing the points first is helpful. F of 2 is what? Somebody's desk is super annoying, but I don't think that's on you. Or it could be somebody's really squeaky pencil. Is it a desk or a pencil that's squeaking? It's a desk. I'll bring WD-40. Okay. F of -1 is not defined. I can't really draw that point yet. So we got that one knocked out. There's that. Now, let's see here. As I approach 2 from the left, so I'm coming this way towards this point, what does the y value have to get really close to? To -2. So it could be a straight line like this. Doesn't have to be. Does this do the same thing as I get really close to -2? Okay. What about as I come from the right side of -2? Or, I'm sorry, of 2. The y value approaches -2 again? Okay. So looks like I'll just get crazy with it. Does this do that? Does that approach -2? Yeah. So we got that one knocked out. The fact that this limit does not specify from the left or the right means it comes and it approaches 0 from which side? Both. So since I already have this side drawn, maybe I'll just do something like this. It's approaching 0 as we get closer to -1. Over here, I'm going to be crazy. Is this also approaching 0? Okay. And then the last little piece, I have my limit. This comes from left and right. How on earth do I show that this is undefined? Two wildly different graphs that have the exact same characteristics when we just look at it through the view of a limit. There's no one right answer. It's a systematic approach is the easiest, best advice I can give you. Okay, we can do more of those if you'd like. What's our next problem, though? 41. Is it the same sort of thing? Okay. Okay, so they give us the absolute value of this, and they say that, hey, this table claims it's 1. As we approach from, I don't know what this question answered. Did you guys get 1? Okay, I'm cool with that. Sweet. Where to next? A. If you're trying, do you have your calculator with you? Can you show me the last line that you typed and gave you error? I bet if you go up, you'll find it. Absolute value on your calculator. Did anybody find it to type it in? What's up? Okay, let's take a look. You guys are going to help me. Do you mind if I put it on? All right, let's see why we have an error. All right, and I scrolled. You had gone up, right, Addison? No, it's the last thing. Okay. So this is, I just went back to home. Oh, you were looking at your table, huh? Where were you looking? I touched your calculator and I picked it up. There's the last thing that we did. What? No, not there. Maybe it didn't save my right because it was an error? All right, so let's check. If you want to type this in as an absolute value, I think it's x minus 5. Anybody dig around and find absolute value on your calculator?
Is it that? I think I saw it.
So I'm not convinced that that's going to do it. It might be, but we should try it because I have the sneaking suspicion that this thing is going to be a such that. But we're going to try it. Let's say we use that bar with x minus 5. Yep, it doesn't like it. It's not an absolute value. But check it out. We don't do a ton of absolute value in here. It makes calculus really weird in a lot of different places. But in the off chance that we need it, I want you to grab your calculators. We're going to find it. And Addison, I'll give you yours back so you can find it too. Okay. If you hit the second button, what's written above 5? Math. Hit second 5. And it's going to pull up like a huge menu for you. My guess, and I don't have it typed in yet, do you see abs? Does abs show up when we hit second 5? Not yet. Okay, we need a number, right? Okay, and I'm trying to go off memory, so bear with me. But I think it's a number, and we're looking for the absolute value. I bet it's there. Absolute value of x minus 5, and then I'm just going to, I could copy this and put it in elsewhere. Again, if you missed it, check it out. Here I am. I'm going to hit second 5, which is math, and it opens up this tab. I'm going to go into number, and I'm going to select number 2. So now if I wanted the absolute value of x minus 5 and I type it in, does that give me the absolute value of x minus 5? Yep. Some of the things are hidden in here, and we'll get practice with it, but that is where your errors happen. On the other side of that, I don't think, and maybe the calculator stuff that we did yesterday was a little bit too much, but I just want to show us something. If we're doing this limit without it, how close do we give me a number bigger than 5. I'm going to show you that we don't actually need it. A little bit bigger. If we did 5.1, I'm just going to use that because it's easy. What would this give me up top? 5.1 minus 5. 0.1 if I did 5.1. And what about the denominator? What's it going to be? Okay, let's get closer. Maybe it's 5.01. It would give me 5.01 minus 5 is 0.01 in the numerator over, what is it there too? We can do this without a calculator. In fact, today's focus is going to learn how do we do these without a calculator. Naturally, you're going to use it. You should get 1, and you will get 1. Are we going to get 1 from the left? Pick something close. Check for me. Think it out. Not on your calculator. Pick something to the left of 5. That's pretty close. 4.9. If we do 4.9 minus 5, it's negative 0.1, right? Well, if it's absolute value, that'd be 0.1 over negative 0.1. What's that limit going to give me? Not 1 anymore. It would give me negative 1. Your calculator can confirm this. If you ask it to do the limit as x approaches 5, it's going to say, no, I can't do it. Because it does that opposite number situation. Not opposite, different. Okay. We skipped to 80 what? AP problems. Okay. The odds. You guys are lucky I was in a good mood yesterday. I don't usually just do the odds. All right. I can't even tell if I'm in the right section anymore. Am I in 1.2? 1.1. Okay. So, AP problems. Here they come. Okay, if we did the odds. Here we go. Number 1 should be Bravo. Number 3 should be Charlie. Number 5 should be Bravo. A is not true because the limit from the left is equal to the limit from the right. Yeah. Yeah. There's a sign out sheet there, okay? All right. Yep, let's look at number 7. I'm sorry? Yeah, let me see what the actual problem's asking. Number 5. 1.1. All right. So on number 5, let's take a look-see. Okay, so here's a piecewise function that they give me. That's nice. They give me a graph. All right. So let's see. We want to see which one is true. If I try to take the limit as x approaches negative 1 from the right, does it have a number that approaches as I get negative 1 from the right? Yeah, I can't see exactly what that number is, but it does approach a number. So I know that that first one, as I approach negative 1 from the right, it's true. Can I approach negative 1 from, I did it opposite, but that's my bad. From the right and left, do we get to the same value? At negative 1. So let's just check. Does it exist from the right? It does, which means this is what? If it does exist, this must be false. Because it says it does not exist, and they're wrong. It does exist. It's whatever this number is, right here. Okay, so that one's false. When you're doing these, I'm not going to do it in my book, and please don't do it in yours, but on your homework, if you want to do it and then erase it, I always go through and I say, all right, that's false. I put an F there. Okay, so we're trying to find which one is true. As I approach 1 from the left, here we go. Is that the same thing as f of 1? Yeah, that one's true. It was asking us to identify the true one. If we've decided that b was the true one, do we need to go further? No, but let's look. Does the limit as x approaches 1 exist on this graph as I get closer to 1, the overall limit? Why? Different numbers. It's this situation, if you look at me. It's this situation that we're running into. That limit does not exist. So C is false because they say it exists, but it does not. And as we approach 4, is the value of the function here the same as the limit? Also false, which we've just reaffirmed. There's only one of these that were true. It has to be B. And they're not trying to trick you on the language, I don't think, but there are some weird ones like which one of these must be true or which one of these could be true. We'll see problems like that. It's very specific in what they're looking for, reading the questions carefully is super important.
For A, I don't understand why it's -1. Because I thought that one was very clear.
So check it out. They're just saying that this limit, as I approach -1 from the right, that it doesn't exist, which means I don't get closer to a value. Here's -1. As I follow along from the right side, do I get to some value? Like the limit does exist. I don't know what it is because I don't have a scale, but it certainly does. It gets closer this way. From the right. You'd have to have a function, like it's hard for us to envision a function that doesn't. If you had a function that got to -1 over here, and it did something like this, like let's say it started waving like this, and then it started doing this really fast, you would never be able to say what it was. That's the only situation that I can think of that we could possibly see right now. Okay. All right. And you said number 7's tough? Or tricky? All right, number 7. Interpret this thing. How did you answer it? Somebody read your answer to 7. It's not multiple choice. You probably have a lazy sentence, I hope. Anybody have a lazy sentence? What happens? What is my function doing as I get closer to 2? It's getting closer to what? 10. From the left and the right? That's it. The function approaches 10 from the left and right as x approaches 2. That's all that this is telling us. The closer I get to x equals 2, the closer my function is to 10. I could word it a bunch of different ways too, but are we okay with that? Okay, name on top. I want them. I don't really want them, but I'm going to take them. All right, we'll pause this because that's going to be an awkward transition there. That doesn't work. But check it out. Today, everybody, we are going to start 1.2. And I'm trying to find the setting that lets me find my cursor because I lose it on this screen constantly. It drives me crazy. All right, we'll go over. Nope. Show me the bar. Nope. Show me the bar. All right. So for today, we are going to be starting 1.2. And there's the cursor. All right. 1.2. Our focus in 1.2 is limits and their properties. Okay. Our goal here is to be able to find a bunch of different limits without having to just blindly type into our calculator. Now, for your notes, we have a couple of options. There are a bunch of theorems that we get today. Not like geometry theorems. We don't prove stuff in here. If you wind up studying math, you will see there's some proof stuff in this book that we just don't utilize fully. But we have two options. We can either go through and list them all out, and I'm just going to show you here because I need you guys' honest judgment. We need a way to get all these rules out, but I don't know that we need to take as much time to write them all down. So on the board here, on the right side is all of our limit properties. The cool thing is that these, for the most part, are going to work the way that you kind of anticipate they will. I don't know for sure. Don't say no just because you don't want to write it all. Should we write these all down like this to make sure we have them? It's probably a good idea. As tedious as it is, here's what we're going to do. We're going to write all the theorems, and we don't have to write them as theorems. We're just going to say, hey, here's some stuff. And then afterward, we'll do examples where we pick which of these properties are we using. Cool. All right. So going through here, our limit properties. I'm not going to give you theorem numbers and stuff like that. We don't need them. But we're just going to start by jumping right in. And we'll talk about some of the names, but we don't really need names. So here we go. We'll just say first thing is theorems. Don't know why I'm writing this word out. I never write it out. Apparently I do sometimes. Okay. For each of these, I'm going to use an arrow to indicate that we're at a new theorem. Now, the first one of these is super nice. We have the limit of a constant is what this is called. This tells us that if we take the limit as x approaches c for something, and I'm going to make the argument of my limit here, and whether it's brackets or parentheses doesn't matter, I'm going to use a capital A. Now, there's no variable, there's no x. If we think of the graph of y equals some number, what does it look like? Y equals 5. What does that graph look like? It's a straight line, which means no matter where we approach on the function y equals 5, what's the value of the function close to? Or at, maybe. 5. So what if it's, instead of y equals 5, it's y equals a? A. Boom. The limit of a constant is the constant. It doesn't go up or down. Of course it's still at the same number. pretty straightforward, I think. Okay, for the second one, let's get crazy with it. We're going to take the limit as x approaches c, and I'm sorry, but I'm going to be able to cheat and you guys aren't. Because I'm just going to do this, and I'm going to copy and paste every time. You guys can't, so sorry about that. I don't know if I did either, to be honest. Let's think about the limit as x approaches c of x. And we're going to, instead of you just listening to me talk for the next 5 minutes, or 20 minutes, however long this takes, 30 seconds with your neighbors, what do you think happens? Think about the graph of that function while you're thinking about it. 30 seconds, talk it out. What should happen? If you're struggling, and I'm going to erase it on the board up there, but I'll do, what does x look like if I want to draw it on this graph right here? The line through here. Not vertical. Y equals x. If it's 1, what's the value of that function? 1. What if it's 2? It's 2. So it just straight up goes diagonally, right? It's just our nice function here. As I get close to some value c, so like at 1, it goes to 1. Easy. At 2, it goes to 2. What about at c? What's it going to go to here? We're done. That's it. The limit of a linear function is just wherever it is. Now, we're looking at the parent function itself, but it's just simply going to be c. It's the parent linear function. Nothing changes. Okay. We're going to get crazy with it, but I guarantee that your intuition will work because I've watched you do this before. Okay. We got another one. Hey, it worked. Okay, so we have the limit of a constant is the constant. The limit of the parent linear function is whatever we're approaching. Let's get crazy with it. Let's say we have two functions. And in this one, we have the limit as x approaches c of f of x. So we have one function named f, and we'll say plus or minus g of x. Now I can think of the exact situation in pre-calc where I asked you guys to finish a statement like this. It's with compositions, if you go back, or combining functions, f of x plus g of x, those sorts of things. Any guess on what happens here? Let's say we had a nice, I'm going to sketch a function up here just so I can do it from here. You don't have to draw the graph. Let's say I have this function. That's f of x. And it does this. And we'll say this is just f of x. Nothing else crazy happens with it. If I approach c, could you tell me this y value? Not a number, but you can tell me what it is. Dolan claims f of c. Does anybody else agree with that? I think so. And as we look at this, as I get closer to it, as long as it's a nice function, which is what we have now, does it approach c from both sides and we're okay? Yeah. So check it out. If we want to know what the value of a function is, a nice continuous function, which we'll clean that up later, I think it's just going to simply be the limit as x approaches c of that first function of f of x. And then what should we add or subtract to this, do you think? Not just c. We did the limit of f, and it's almost like it's just distributing it, is what it looks like to me. The limit of f plus or minus the limit of g. Now, we'll see here in a couple minutes that picking out where that is really easy to do if our functions are nice, and we get all nice functions. Now, these all have the ugly language that we talked about with sums. The limit of a sum is the sum of the limits. That's how we can say this. The limit of a difference is just the difference of the limits. Okay, let's see if our powers of deduction are ready to kick in yet. And if I'm going too fast, because obviously you're trying to listen and talk, and I'm trying to get through it all, don't hesitate to tell me to pause, and I can chill out for a minute. Okay. Gut feeling. What if I have those two nice functions again, but instead of adding or subtracting, I multiply them? Gut feeling for how this might work? F of x times, love it. All right. Is there any surprise with any of these yet? Okay. The limit of a product is the what? Here's a limit of a product. And it's the product of the what's? Limits. Yeah, that's it. It's that same phrasing happening again. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. So forth and so on. All right. We only have a bunch more. So that's good news, I guess. We're just going to like blast through these and then we'll stand up as soon as this is done, okay? Cool. All right. Let's say we have the limit as x approaches c, and I'll just write it since you guys are writing it too, of some constant k, and I'm going to put the argument in here, k times f of x. Now, we're going to try to default back to some log stuff. Where do constants go in logs? And let me rephrase that. I don't like that. Never mind. Disregard that last comment. If you wanted to take something out of this, what makes sense to you to take out? The k. It'd be weird to take out just the f or just the x, right? But the k is a constant. If I have some function that's being multiplied by a scalar, this k here, turns out, just deal with the easier function. Let's just do it as k times the limit of f. Where can we move constant multiples in a limit, apparently? Move them to the front. Makes it easier. Now, whether or not you actually do this depends on the problem, because sometimes it's just as easy to leave it in. But if you have a constant, just take it out. Easy enough. Okay. No, we're just going to keep kicking. All right. Love it. Let's say we wanted to take the limit as x approaches c of, and I'm going to make an argument here with a nested parenthesis. Let's say we had like f of x, and that thing got raised to the nth power. So we already had a function, and we're trying to take its limit, but we raised that function to the nth power. Now, for these, if you're just dying to prove them, I'm not super opposed to this, just so you guys know. But this exponent can also move around a little bit. This one's a little bit stranger than the others. We're going to say that this is just the limit of the function. Then everything gets raised to what power, do you think? To the n. Okay. Anybody in here stressing out already? Like, oh my god, I have to memorize so much stuff. You will get these by virtue, like, I bet 2 or 3 days you'll have these locked in. Whether you can actually say them or not, irrelevant. You will have a natural feeling for how to do limits because these properties are handy when they get hard, but we're not at hard limits yet. We're just going to do little by little. Okay. Let's see here. Only a couple more that we really need. You think square roots work with this too? Like if I had the square root of f, would the same rule apply? I'm going to make the claim, don't write this one. I don't think we need to write this one, but I want you guys to tell me why. And we're going to move this a little bit. You guys, instead of talking with your neighbors, you're going to stand up and go see if you can't convince somebody else that we don't need to write this rule. Okay, stand up, move, go talk to somebody. Why don't I write this rule based on what I wrote in the previous? Everybody stand up, move. If you talk to the same people, if I'm just standing up, I'm okay with it. But get up, move a little bit. Why aren't I going to write this rule for us? What do you think? Why is it the same? Is that an exponent? Even though we don't write it, square root. What exponent? And if we have an exponent, we already have a rule for it. So this is just that exponent rule. It just looks like a square root. Okay, I heard you guys say it. Why don't I need this rule? I heard somebody up here say it, and I know that you guys know it, but Red, you've given me a bunch of answers, which I'm not trying to dissuade you from answering. Karina, I think I heard you say a word that says why we don't need this rule. Follows the pattern. What pattern do you see? Like, what do you mean? Okay, I kind of like that. I think we can be a little bit more specific. Could I write the limit of the square root differently? Like, give me a different way to write a square root. To the 1/2 power? Is that the same as if I just took this and did this? Is that the same thing? Do we already have a rule for if there's an exponent? We don't need another rule. It's the same rule because it's the exponent. Cool. All right. So I'm not going to do the rational exponents. either then. And let's check it out. We have 2 more is all we're going to write here. So you guys are 3 more that we're going to write here. 4, just kidding. There's only 3. Okay, let's take the limit as x approaches c. And I'm going to have a couple more words on this one. We're going to make our argument p of x. And then underneath I lied is where I'll write this. And I'll say where p of x is a polynomial. Now, the reason that I want to stress that this is a nice polynomial is because polynomials can be drawn with smooth curves and you never have to pick up your pencil. Like, I started alluding to this earlier and then I didn't kick forward with it. But if you give me any polynomial function, which means it's continuous, you can draw it without picking up your pencil, and it's smooth and curved, then all we need to do, and we're going to see if we can't logic this out here, here's this function that's smooth and continuous. As I get closer to this value, the y value gets closer to there. A few minutes ago, Dolan helped us pick out what point that was. If this is my function p of x, what value does this get close to as I approach c? P of c. Boom. This here has a name. This, I'm going to make a little star here. There's not many of them that have names. This is going to be like our method to solving limits. This is what we call direct substitution. It is always going to be our first step in solving a limit problem. The very first thing that you're going to do is you're going to just try to plug it in. If it spits out a nice number at you because you're working with a nice function, then you can be assured that we have the right limit. Anything that's smooth and continuous, we just have to ask the function, what is your value here? And that's what we approach as we get close to it, like it's the same number. Okay, last one. Oh, question? Yeah, I'm actually up to champion now in Rocket League. Thank you for asking. That's a good point. I didn't want to highlight that outside of asking, but somebody asked. So, all right, last one. What if we have the limit as x approaches c of, let's say we have a function f of x divided by g of x? How on earth do we evaluate this limit? Davian, I don't think I've called on you since we've been in school. What's your gut say? You can not say x, you can do it without x approaches. You can just say limit. Love it. Anybody else have that gut feeling that it was just going to be the limit of f of x, I suppose, over the limit of g? Okay. These are the limit rules. Now, there's very few situations where we're going to have to get really crazy with them. These, as far as like stuff to memorize, I would not say are up there with the top priorities. Right now, we need to know at least how to use them. You won't have to memorize them because most of them are going to fall right into this category, or they'll fall into a category like adjacent to this that we'll look at how do we deal with them. So, with these, we have all of our properties. I think we should do some examples up on the board. So I'm going to zoom out a skosh, or a lot. Can you guys still read that on one of the boards if you're standing next to it? Okay, maybe not from like the back seat. You can't. But all right, we're going to do some examples. If you want to take your notebooks with you, like you're free to do that. But we are going to go with the one person holds a marker type of situation. And let's see, examples feel blue to me. So we'll change that. Okay, I want you guys to go up to a table. If you're going to take your notes, take them with you if you want to. Don't have to. But you guys, I said table. Go to a board. We'll get some examples going. So for these examples, I'm going to change color because I don't like that one. Dark blue. You can erase anything that's on the boards. Yep. Okay, we're going to say this is just evaluate each limit. Okay, your job, every time between each problem, you're going to talk with your partners, you're going to switch markers, explain it. If you're struggling, obviously the person with it can talk, but I don't want you to just get up there and solve the problem for everybody else. Okay, so we're going to bounce around in no particular order. I want on A, the limit as x approaches, let's say, 2 of x squared. And I'm going to start listing some more. We'll lose our properties here in a minute, I would imagine. But I want you guys to try that one. X approaches 2. Yep. And I'm going to get a bunch more up here, so don't worry. Yep. I'm going to let you guys start, and then I'll add more. Don't worry. But we'll do with these three first. As we're looking at these, reminder, and this is super important because you're going to hear this about a million times in the coming days. What's the first thing that we should try? So that was awesome, but that was only 2 of the 12 in here. One more time. What's the first thing that we should try? Direct sub, 100%. Now, if you want to direct sub, we can. I see some of you guys using like the properties and expanding it all the way out, which I love that I'm seeing that. Let's take a look-see. If we wanted to expand this, the first property that I see is it becomes the limit as x approaches 2 of x, and then what happens to all of it? If I have an argument that's squared, it just moves, right? Okay, do we have a rule that says, hey, the limit of this linear parent function? It's just whatever this is, yeah? So it looks like if we go one more step, there's our first line if we're expanding it fully. The second line is 2 squared, which gives me 4. Now, this is using the properties and expanding it all the way out. Maybe we don't need that every time. What's the first thing we should try? If we direct sub and we just sneak a 2 in right off the bat, what's 2 squared? We're done. Cool. There's the shortcut where we just say, hey, this does happen, and I know it happens. Or we can go through the properties and see like, yeah, okay, it does happen. This one, we have a few different routes. Now, I'm kind of between a rock and a hard place because I don't like writing a ton of stuff. And I don't think you guys do either. But I see a ton of stuff going on. The first step that I wanted, I have the limit of something that's squared. We could just say it's the limit of something, and then all that gets squared. Okay, we could expand it out. Now, I'm going to do 2 expansions. I lied. I'll do it this one. The limit as x approaches a of x squared minus 2x plus 1. And all that now gets what? Squared. That's that property that allows us to move our exponents. Now, if we wanted to expand this further, could we? What's the limit of a sum? The sum of the limits. So I'm only going to write lim because I'm lazy. I'm not going to do the x equals a part, okay? We could have the limit of, what's our first piece? X squared, and we're going to take 2 steps. The next one would be the limit of 2x, right? But pause, because 2x kind of looks like kf of x. What could come out of this second limit? Is there a constant multiple? 2, the limit of x, plus 1, the limit. I'm going to do the x approaches a because it looks like ln when I do it otherwise. And then could I still square this whole thing? Okay, if we do that, and we're just going step by step, let's just see what we get. It should be the limit as x approaches a. Can you possibly tell me why I didn't think to write it? What's the limit of a constant? The constant. So in my head, I just already skipping a line ahead. I didn't. Thank you for calling me out. Okay, well, help me out. What happens with this a? Where does it get plugged in? Now that we have this simple one, this just becomes what? A squared. This one, I have a 2 out front, and what's the limit of x approaches a of just x? A, okay. Plus, what's the limit as x approaches a of 1? And then what happens with this? We're done.
Why is it 1 not A?
Why is it 1 not what? Because remember, x approaches a, right? If I have the limit as x approaches a, and I'm going to write this nicer, of 1, show me where you're going to plug in a for x. Yep, and like, good question, because that's an easy thing to get goofed up on. Okay, I just want to look here real quick. What would have happened if we just tried direct substitution first? I would have, like, is this a polynomial? It's smooth. It's x to the fourth plus some other stuff, but it's a nice polynomial. And if it's a nice polynomial, what can I just do? Use different language. You're right. I do just plug in a, but we say we direct sub a squared minus 2a plus 1 squared. We're done. The properties are there to justify that we can do these things, but look at how quick that goes. This one, oh, go ahead. Yeah. Is this a polynomial? Can we direct subpolynomials?
Yes.
And if we just put a in, what do we get? A squared minus 2a plus 1 squared. Okay, this one, I was trying to throw you for a loop. Pi is a what? Number. Does it ever change? No, so it's a constant? What's the limit of a constant? The constant. We're done. Okay. I'm going to do you guys a solid. I'm going to put the 2 days of homework together tomorrow because we're going to start tomorrow with fun limits. The homework, not really an assignment, but practice F words. I would look back at your notes from factoring stuff because we're going to be factoring tomorrow. You're going to be factoring a lot. We're going to be rationalizing a lot. Cool.